Hello.
Hey, this is Gundan.
Hey, this is
Agarwal.
Gundan.
Why use I-beam in construction?
What is the most common shape of beams that you see in all these structures? It's the famous I-beam. As you can see over here, it's called as the I-beam as because of the cross-sectional spells out the capital letter II. But why do engineer prefer this particular shape? Why not any other alphabet? Why not? Suppose we wanted to build a bridge which is supported at its ends, and let's say we start out with a bridge having a rectangular cross-sectional due to various forces which are acting on the bridge, like somewhat gravity is pulling downward on its own, weight is pulling downward on it, and there are other things on the top of this. Maybe there could deform. Now the exaggerated this bending over here, but it does. We have already studied that materials deform under external forces, alright, and when they deform they try to snap back and do that. There are restoring forces generated inside, and as a result this whole bridge now is under a lot of stress. And we have also studied that if the stress goes beyond a particular value, if you deform it too much, then the whole thing can even break. And the whole question, we don't want this bridge to break.
Studied that materials deform under external forces. Alright, and when they deform, they try to snap back, and to do that there are restoring forces generated inside, and as a result this whole bridge now is under a lot of stress. And we've also studied that if the stress goes beyond a particular value, if you deform it too much, then the whole thing can even break. And the whole question now is, how do we resist this bending? That's the big question. We don't want this bridge to break, we want to resist the bending. So how do we do that? Well, we can start with our intuition. We already know that if you have a thin stick like this, then it's quite easy to bend and break it. But on the other hand, if we had a very thick stick, then it's more difficult to bend it and it's more difficult to break. So a very simple thought that we could have is we just make this bridge thicker, right? So you take this bridge and make it thicker. Just make it thicker and we are done. Well, but there's one problem with this. If you make the bridge thicker, then you're using more material and you're increasing the weight of the whole thing. And if the weight increases, the bending force further increases. So that's a problem. And not just that, then our support has to be strong. And then if you want to carry this from one place to another, so if you're manufacturing it in one place and then you're transporting it to another place, then again that becomes more difficult. So there are a lot more problems that are introduced when you make this bridge thicker. So you're creating more problems than solving it. So you know what would be a great thing to do? We want to find a way to make the bridge thicker without increasing its weight, without adding more material to it. And at first you may be like, what? How do we even do that? Right? So engineers were faced with this problem, and initially it feels like it's not possible. But if we dig into the physics of it, then we can come up with a solution. So the key is to understand exactly what kind of stress is generated inside such a bent beam. We've learned a couple of kinds of stresses. We've learned about tensile stress, compressive stress, shearing, bulk stresses. We've learned about those in previous videos. And if these things sound new to you, then maybe it would be a great thing to go back, watch those videos, especially tensile stress and compressive stresses. Those are going to be important over here. Watch those videos and then come back over here. You'll be able to appreciate this much better. But anyways, in any of those videos, we never spoke about bending like this. So it might seem like bending is a little bit more complicated, and it is, but if we look at it carefully, we can actually understand what kind of stress is generated over here. To do that, we'll look at this bridge one more time. But this time, let's imagine some hypothetical imaginary sticks that we have put, imaginary rods that we have put inside. These are going to help us understand how the stress is. And now, again, due to the force, when the bridge deforms, notice that the sticks come closer to each other on the top and they go farther away from each other on the bottom, which means on the top the molecules must have come very close to each other. That's what these sticks are doing. They're helping us understand what happens to the molecules. The molecules must be coming closer to each other on the top, and the molecules must be going farther away from each other at the bottom. So at the topmost point, the molecules are the closest. Just like how the stick are the closest at the topmost point, the molecules over here are the closest. And remember, when the molecules come close to each other, we're talking about compression. Can you see that? The sticks over here, since they have come close to each other, this top part is actually under compression. So this part over here is under compression. and there's maximum compression at the topmost part over here. So there's a lot of stress. There's a lot of compressive stress, maximum compressive stress on the top. But notice, just like how the stick goes far away at the bottommost point, the molecules have also gone very far away from each other, and therefore at the bottommost point, we have maximum tensile stress. The molecules are going farther away from each other, so there's tension going on over here. So there's maximum tensile stress. Maximum tension, we would say. So again, a lot of stress is over here. And notice, as you come closer and closer to the center, the compression decreases. And similarly, as you come closer over here, tension decreases. So the closer you go towards the center, the compression and the tension decreases. And pretty much at the center, there is no compression or tension. And so we could say there is no stress over here. No stress at all. Now we'll go back to our intuition. Why is it that when we make the stick thicker, it is difficult to break? Well, that's because when you make it more thick, you're adding more material, you're adding more resistance to bending because there'll be more restoring forces, and that's why it becomes more difficult to bend it. But guess what? If you want to resist bending over here, you only require more material on the top because that's where compression is going on, and you also require a lot of material on the bottom. But you don't require a lot of material in the center because there is no stress, there is no resisting forces set up in the center. So why waste material by putting it in the center? And that was the idea that engineers came up with. And so engineers said, well, we can make the whole thing thicker like this, but not by adding more material. All we have to do is remove the material in between because they are not going to provide any resisting forces. So let's not waste our material over there. So let's remove all the material from this center. Let's get rid of all the materials over here. Let's remove them. Let's keep it very thin at the center. And let's put all that material at the top. And notice, as a result, the shape that you end up with is the I shape. And this is the famous I-beam. So what we have done is we have made it thicker in the regions where the stress is maximum, thereby making it very hard to bend. But we have not used any more material than we were using before, so the weight of this is pretty much the same as before. And that's why engineers say that this is the most efficient shape to withstand bending. And therefore, I-beams are awesome.